Now in this video, I'll be shortly talking about Rayleigh-Jean's law, which was able to calculate the energy radiated by a hot body in some frequency range nu and nu plus d nu. And then after that, I will try to continue with the Planck's black body radiation law. Now, this Rayleigh-Jean's law, what it does, it basically calculates the energy radiated by a hot body in a frequency range of nu and nu plus d nu. And the number of independent vibrations or the degrees of freedom per unit volume with the frequencies from nu to nu plus d nu, he comes up with an expression equal to 8 pi nu square d nu by c cube. Now, this is simply the number of these independent vibrations, or may call them degrees of freedom, and and he was able to calculate the energy associated with each degree of freedom. Energy associated with each degree of freedom. And what was that? How much was that? That was calculated to be 0 to infinity e to the power of minus e by kt dE, divided by 0 to infinity e to the power of minus e by kt dE. Now, the results of this energy associated with each degree of freedom, when this thing is associated with the number of these independent vibrations, it was evaluated by evaluating these equations, that the energy over a frequency d nu, it comes out to be 8 pi nu square by c cube kt and d nu. Now, what is this kt? Is a result of the evaluation of the expression that's here. This kt is this k is the Boltzmann constant and T is the temperature. So this is the result basically that's obtained by Rayleigh-Jean's law. I'm not going into the details of discussing this Rayleigh-Jean's law, because my intention is to go with the quantum nature of radiations. So this is the equation that's being the result that has been obtained by Rayleigh-Jean's. And now, according to this expression, the energy that's emitted by the black body, you can see it increases. It increases with the frequency. Okay, it increases with frequency and becomes infinite at large frequencies. You can go on and on with this equation. And what if we go back to the black body radiation law? The curve is like this. This is what is experimentally measured. And if this is the frequency and this is the energy in terms of the frequency, this is what is obtained. But as per this equation, the energy is going to increase. It's going to increase from this equation point of view. So we can say that from this experimental curve, it shows that the energy radiated at particular temperature becomes zero. It becomes zero for both at lower as well as higher frequencies, right? Uh, but that's not the case here. And if we want to write down the energy carried by all the frequencies that are there, then suppose that energy is E. That will be the integration of this E nu d nu, and it will move from 0 to infinity. So you will have this 8 pi nu square by c cube kt 0 to infinity. This will give us the energy due to all frequencies that are available there. So the value of this integral is infinity for any value of t other than that of t equals 0. So this physically means that the total energy that's emitted by a black body per unit area per unit time is infinite at all temperatures. It is infinite at all temperatures, and clearly this is entirely the false conclusion. And both the above equations, this equation and this equation, what we conclude from these equations is that these equations are incorrect when we compare these equations to the actual black body spectrum that's being drawn out here. So both of these conclusions are incorrect and fail completely to account for the observed spectrum that we have, spectrum of radiation emitted by this black body. And the frequency distribution of the black body could not be explained on the basis of the classical concepts, because this Rayleigh-Jeans law, it goes exactly with the classical intuition, where energy is continuously radiated, or energy is continuously absorbed by the black body, and the results that are obtained here, they are inconsistent with what is experimentally observed in the black body radiation experiment. So this problem was resolved, and this discrepancy in classical calculations, it was observed, and it was removed by Planck, Max Planck. On the basis of quantum theory. Now, what were the assumptions of Max Planck? So now we would like to go with Planck's black body radiation law. So to start with, we must have some approach of understanding, because what were the basic assumptions that were formulated by Max Planck. And Max Planck, actually, he was able to obtain an empirical formula to explain the result that we have for the black body radiation law. And the formula that was deduced using deduced using some basic assumptions, and these assumptions we call as Planck's hypothesis. Planck's hypothesis. So point number one, as long as the assumptions are concerned, is that a black body radiation chamber is basically filled up not only with the radiations. There are not only radiations inside the black body, but there are also but there are also simple harmonic oscillators inside the black body. So there are oscillators inside the black body. And these oscillators are also called as resonators. So there are simple harmonic oscillators, and they are also called as resonators. And they have molecular dimensions, and we call them as Planck's oscillators or Planck's resonators, which can vibrate, and they have they can vibrate with all possible frequencies, and the vibration of the resonator entails 1 degree of freedom. It's one vibration leads to 1 degree of freedom only. The next important assumption is that these oscillators, these resonators, they can radiate. They can radiate. Okay, they can radiate or they can absorb. They can radiate, absorb energy continuously in the form of packets, but they are not going to radiate or absorb energies in the classical way. They are going to absorb and radiate in the form of packets of energy, in the form of quantas, in the form of photons. And these oscillators who have the frequency nu can only radiate or absorb energy in the units of photons, or you can call quantas, or you can call them packets of energy. So this assumption is clearly deviating from the classical concept of continuous absorption of energy. Energies. And the magnitude of this energy of photon is given by this h nu, where h is the universal constant known as Planck's constant. And its value, we know what's the value of this Planck's constant. Now this assumption is most revolutionary in character. This assumption that these harmonic oscillators in the black body, these resonators, they absorb energy in the form of quantas, in the form of photon energies, in the form of h nu. This is the revolutionary transition. Now, in other words, what it states is that the exchange of energy that we have between radiation and matter, right, it cannot take place continuously, but they are limited to the discrete set of values as 0, h nu, 2 h nu, 3 h nu. There is nothing in between. These things are continuously absorbed, but in the form of quantas, in the form of these packets of energy, in the multiples of some smaller units called quantum. Now, what's our intention is based on these assumptions. We would like to derive this Planck's black body radiation law, and to start with, what we assume is that we shall first be in a position to find the number of resonators, the number of resonators per unit volume. Okay, lying in the frequency range of nu and nu plus d nu, which I already introduced you when I was talking about Rayleigh-Jean's law, where using those ideas of how to calculate this number of resonators and the number of modes of vibrations that we have per unit volume within the frequency range of nu and nu plus d nu. It is 4 pi nu square d nu by c cube. And now what we are talking about, now the black body radiation travels with the speed of light, right? And this, it has transverse nature. So if it has transverse nature, unlike sound waves, therefore it has two states of possible polarization states. So if we multiply this number with 2, then we are going to get the exact number of modes of vibration of these transverse waves, and that comes out to be 2 times 4 pi nu square d nu by c cube. So this is 8 pi nu square by c cube d nu. Now, moving forward, now let's talk about the average energy of a Planck harmonic oscillator. So what should be that? Average energy of Planck's oscillator. So let me assume that is E, that energy is E, and that will be the energy of each oscillator divided by the total number of oscillators that we have. So we would like to start from this equation, and what we would like to do at this point of time is to make use of Maxwell's distribution law, Maxwell distributions law. So moving ahead from here is that according to Maxwell law of molecular motion, what we have is, if we have some E is a certain amount of energy, then the probabilities that the system will have energies 0, 2E, and so on and so forth, RE. These probabilities are in the ratio of 1 is to e to the power of minus E by kt is to e to the power of minus RE by kt. So this is how the ratio of these probabilities go. Now, if I assume that N0, if N0 is the number of resonators having zero energy, okay, and N1 having N1 number of resonators having E energy, what will be the number of resonators having E, having energy E? Their number will be E. It will be N0 e to the power of minus epsilon by kt. Now, in the similar way, if I take N2 for the same kind of considerations, I will have 2E here, and that will give me N0 e to the power of minus 2 epsilon by kt. And so on and so forth. This is how this thing will move on up to NR. So what will be the total number that I'm talking about? That will be N0 plus N1 plus N2 plus so on and so forth, NR plus so on and so forth. And I can immediately use the values for these N0, N1, N2, and R. So what will N come out to be? That will be N0 plus N0 e to the power of minus epsilon by kt plus N0 e to the power of minus twice epsilon by kt plus so on and so forth. This is how this series will go on. Now, I can immediately think of getting N0 out. What will remain inside is 1 plus e to the power of minus epsilon by kt plus so on and so forth. This is how this thing is going to. So then I'll have here e to the power of minus twice epsilon by kt and so on and so forth. So this N will be N times 1 plus y plus y square plus so on and so forth. And this series can be approximated as 1 plus y square plus so on and so forth as 1 by 1 minus y. So n, which is basically the total number of oscillators in all formats, that will be n0 by 1 minus y. Now I would like to call this as equation 1. And now talking about the total energy of these, total energy of Planck's resonators or oscillators. Now that energy will be E, that will be 0 times N0 plus E times N1 plus 2E times N2 plus so on and so forth. This is how we can calculate the total energy of all the harmonic oscillators. So this E will be E times N1 plus 2 times E and N1, this is N1, this has to be N1 in terms of N0 will be N0 e to the power of minus 2 epsilon by kT plus so on and so forth. This is how it will go like. And proceeding from here, this is my equation 1 and this is my page 6. So what should I do from here is I would like to write this E and get this, this is N0 e to the power of minus epsilon by kT. This is minus 2e and this way it will move on and on. So if I think of getting N0 out, this E out, what will be left inside is e to the power of minus epsilon by kT plus 2e to the power of minus 2 epsilon by kT and plus so on and so forth. This is how this series is going to go. And I can use here N0e times. Now this is my y plus this is going to be 2y square and then plus so on and so forth. This is how the situation will go like. Now to make a simple modification here, if I assume that this S, I will take some quantity, say P, and this P is equal to y plus 2y square plus 3y square plus so on and so forth, and I multiply this equation by y, I will get Py. I'll get here y square plus then I will get so on and so forth. So this will be 2y cube plus so on and so forth. And if I subtract the two series like P minus Py, I will obtain this y, then 2y square minus y square, here it must be cube. It will give me y square, and it will give me this is going to give me y cube. So this is y square, then I'm going to get y cube and so on and so forth. That should be the case. And if I have P out, this is 1 minus y equals now this thing is my this is y plus y square, and this series can be approximated by y by 1 minus y. So that implies this P is y by 1 minus y whole square. Now this p has come from this equation, so this whole thing is p. So what is E going to be? Now from this we have this E, so E is n naught E times y by 1 minus y whole square, and this is my equation 2. And if I go back to my equation where from I started, where is that? So I have two equations. This is equation 2, this is equation 1, and okay, and this is E. So this E, I should call it E1 or EX, otherwise it will cause problems. So this is EX, okay? So this EX is E, it is E by N, and what is E is N0 E y by 1 minus y whole square times 1 by N0. This is divided by N0 by 1 minus y. There's a lot of confusion. So this is this energy is there will be the reciprocal, this n naught and n naught will cancel, this 1 minus y and square will cancel. So what will be left with is a y divided by 1 minus y. Okay, so this will be the average energy. I think it will be appropriate if I use a bar here. So this is my what is the average energy of the resonator. The average energy of this resonator is like this. But what is basically y? Y is what is y? Y is e to the power of minus epsilon by kt. Now, if I think of using that here, this is epsilon e to the power of minus epsilon by kt divided by 1 minus e to the power of minus epsilon by kt. Now, multiplying and dividing by e to the power of epsilon by kt will give me, because this will go, I'll get 1 out of it. So what will be the average energy of the resonator? That will be E divided by e to the power of epsilon by kt minus 1. So this is what we achieve from here, and according to Max Planck's hypothesis, this quantum of energy E that we have here as epsilon, it is nothing but h nu. So the average energy of the Planck's oscillator, let me put a bar here, it is h nu by e to the power of h nu by kt minus 1. Now the point is that there is a range of frequencies, and the energy density belonging to the range d nu can be obtained by multiplying this average energy by the Planck's oscillators, by the number of oscillators per unit volume that we have already calculated in the frequency range of nu and nu plus d nu. So we have that equation. What is that? number. Where is that number? Yeah, that is 8 pi nu c. What was that? Yeah, it was 8 times. Yeah, it was so here I'll have E of nu, d of nu is 8 pi nu square by c cube. Uh, then multiply this number with this average energy h nu by e to the power of h nu by kt minus 1 d nu. So this is the energy. This is the Planck's black body radiation law in terms of frequency. And this E nu d nu is basically this is energy density now. This is energy density. That's the total energy per unit volume belonging to this frequency range nu and nu plus d nu. Now we can translate this Planck's black body radiation law in terms of wavelengths also. So for that, what we have to do, we have to make use of nu equals c by lambda. So d nu in that case will be minus c by lambda square d lambda. So if we take the magnitude of this, so that will be c by lambda square d lambda. Now if we think of using this and translating this formula, we have e lambda there and d lambda. So this will be 8 pi nu square. This is nu cube basically. So nu cube will give me c cube by lambda cube, right? And c cube, the original c cube is here. Then I can have here h, no problem with that. Divide by e to the power of h. Nu is c by lambda kt. Okay, minus 1, and this d nu is it is c by lambda square d lambda. So we can write down e lambda d lambda is yeah, this is c cube here. C cube and c cube will go. So this is 8 pi h by lambda square times 3. It is 5. Okay, hc is here, and times 1 by e to the power of hc, e to the power of hc by lambda kt minus 1 d lambda. So this is this is Planck's black body radiation law in terms of wavelengths. Now if I proceed from here also and go with some approximations, like if I take the case of short wavelength. Now for short lambda. Now for short lambda, this one can be neglected for short lambda, and we can have this Planck's black body radiation law boiled down to E lambda. This is average E. Okay, committing some mistakes. Sorry for the mistakes. So d lambda is yeah, what is it? It will be 8 pi hc by lambda 5 e to the power of, this will go up, minus hc by lambda kt d lambda. Now this is what is called as Wien's law. So we have here Wien's law as an approximation of black body radiation law in the shorter wavelength mode. Now if for the same case for longer wavelength, so for lambda large, for large lambda, this whole thing can be approximated as e to the power of hc by lambda kt minus 1 can be approximated as 1 plus hc by lambda kt. Now if we do that, where will we go from there is that this E average lambda, the lambda will be 8 pi hc by lambda raised power 5 Yes. Then here 1 by 1 plus hc by lambda kt minus 1 d lambda is here. So this plus 1 and minus 1 will cancel, and this h will remain here, and lambda kt can go up. And then what we'll obtain, so E lambda d lambda will be 8 pi hc by lambda raised power 5, and this lambda kt will go up, divide by h will stay here, right? And d lambda will stay here. So we can see this lambda and this raised power 5 will convert into raised power 4. What we will have is E lambda d lambda is this h, and h is going to cancel. This is 8 pi c by lambda raised power 4. Then we have k, and then we have p. And this is, if we translate it in terms of the frequency using the same relation, nu is equal to c by lambda, converting from lambda to c by nu, this is your Rayleigh-Jeans law. This is Rayleigh-Jeans law. So we can see that that both laws, Wien's law is valid for shorter wavelength, and it's merely the approximation of Planck's black body radiation law, and Rayleigh-Jeans law, which is valid for large wavelengths, is merely an approximation of Planck's black body radiation law. So this was the greatness. This was the great job that was performed by Max Planck to resolve the problem of black body radiation law by assuming that the energy that's absorbed by a black body, or the energy that's radiated by a black body, it is absorbed or radiated in the form of quantas, and the atoms that are present inside that body, they are acting as harmonic oscillators, and each of these harmonic oscillators can absorb energies in terms of quantas, in terms of h nu, 2 h nu, 3 h nu, and so on and so forth. And this is how a revolutionary transition was there in explaining the phenomenon of black body radiation law, which classical physics completely failed to explain the spectrum of this black body radiation that was conducted experimentally. So with this, I might have committed some mistakes. I'm sorry for that. You can do better than what I have done, and you can do the corrections wherever I have committed a mistake. So with this, goodbye and good luck.